Hello, here's a screencast for sections 1.4 and 1.5. So the first topic is 1.4, it's compositions of mixtures. There's not that much stuff to know from this topic. First thing is know what a mixture is. A mixture is defined as something with a variable composition. There's two classes of mixtures. There's homogeneous, which has visibly indistinguishable parts, as in it all looks like the same thing. You cannot see the different parts. Examples are any solutions such as air, brass, so like salt water would be another example with that. A heterogeneous mixture has visibly distinguishable parts, as in you can see the different parts. So examples would be cement, gravel, Chex Mix, chocolate chip cookies, things like that. So with this, just know the definition of each type and know a couple of examples of each. Okay, so along with this, here's a sample question from this part. Elemental analysis can be used to determine the relative number of atoms in a substance and determine its purity. So the example is a student has a sample of FeCl2 or FeCl3. They're not sure which one. They can determine the mass of iron in the sample. So can they determine if the sample is FeCl2 or FeCl3? So first of all, you kind of want to think about, well, what are the differences between FeCl2 and FeCl3? Well, the answer to that is really, there's a lot of differences. They're different compounds, so they're going to have different properties, different physical properties, different chemical properties. Okay, got interrupted there. So I was saying FeCl2 and FeCl3, they're different compounds and they're going to have all sorts of different chemical and physical properties. But what we're looking at here is mass, all right? So what we're going for here is that FeCl2 and FeCl3 are going to have different percentages of iron by mass in the compound. So FeCl2 is going to have a higher percentage of iron than FeCl3, just because there's 3 chlorines in FeCl3. So that has a higher percentage of chlorine, lower percentage of iron. So we can determine, if we know the mass of iron in the sample, we can assume that we can also find the mass of the sample. That allows us to calculate the percentage of iron in each of those compounds. FeCl2 and FeCl3 have a specific percentage of iron in the compound. It's the law of definite proportions from an earlier section. So we could just compare our measured percentage to what FeCl2 and FeCl3 are, and that can tell us if it's one or the other, or if it's a percentage in between those two, then it would be a mixture of those two compounds. So in red here, this is what I would put down for the answer. Yes, if they can determine the mass of iron, the percent by mass of iron in the sample can be determined. FeCl2 and FeCl3 have different percentages of iron, so you can compare the percentages and tell if the sample is one or the other or a mixture of the two. Okay, next, topic 1.5, that's on atomic structure and electron configuration. So you want to know a little bit about the basics of atomic structure, like the subatomic particles. We don't have to go too deeply into those concepts. What I have listed here is really about all you need to know. Now there is a lot of stuff about electrons and how they behave, so we'll expand on that a little bit. We start the modern view of atomic structure. It has electrons. They're found in the electron cloud, which is the area outside of the nucleus, and they have a -1 charge. Protons are found in the nucleus. They have a +1 charge. Neutrons are also found in the nucleus. They have no charge. And then you have isotopes, which we talked about those a little bit before, but those are atoms with the same number of protons but different numbers of neutrons, so they have different masses. Okay, and then we have the atomic number, which is, we use Z to represent that. That's the number of protons, and you can find that on the periodic table. And you also have the mass number. The mass number is the sum of the protons and neutrons. Now with this, we can create an atomic symbol. So the symbol looks like this. X is the chemical symbol, you know, the 1 or 2 letter symbol for the element. We put the atomic number to the lower left. You put the mass number to the upper left. If there were a charge, and it doesn't show any here, but if there was a charge, you would put it to the upper right. So now with this, we want to be able to determine the number of subatomic particles from the symbol. So there's 2 examples here. So this first one, we have carbon. Okay. Now if this bottom number here wasn't listed, if it was absent, you can get that from the periodic table. Carbon's element number 6. So this atomic number, that tells us the number of protons. So this has 6 protons. To get the number of neutrons, we take the mass number minus the number of protons. So in this case, 12 minus 6, so you're going to have 6 neutrons. For the number of electrons, we have to factor in a charge. So with nothing here, that means it's just a neutral carbon atom. That means the protons and electrons are equal. So for this first example, there's 6 protons, 6 neutrons, and 6 electrons. For the other example right here, you have the chloride ion. We have a -1 charge now. So the bottom left number, that's your atomic number again. That's your number of protons, so that's 17. 36 minus 17, so that's 19. That's your number of neutrons, mass number minus atomic number, that's your neutrons. And then for the number of electrons, now you have to factor in the charge. So if it's a -1 ion, that means you added 1 electron to the atom. So now you go 17 plus 1, now you have 18 electrons. So if you have a negative ion, that means you've added that many electrons. If it's a positive ion, that means you took away that many electrons. So there's the answers there. Okay, next is Coulomb's law. So Coulomb's law is something that we'll see a lot throughout the year. It's used to calculate force between 2 charged particles. The equation is here. It's Q1 over Q2 over R squared. Q is the charges. R is the distance between the 2 particles, or radius. So you see an example over here. If the particles have opposite charges, that means this Coulombic force is going to be an attractive force. If the particles have the same charge, then it ends up being a repulsive force. But it's all based on this equation right here. So this means that the force between particles is proportional to charge over distance. And really, I would underline that right here. That's really all we need to know with this. It's charge over distance. As in, we won't do any calculations with this equation. So you're not going to actually use that equation. All we do is estimations and comparisons. So we just need to know that a Coulombic force is proportional to charge over distance. So if we have higher charges, that means a stronger Coulombic force. As in, if you take calcium with a +2 compared to sodium with a +1, calcium is going to have a stronger Coulombic force. If you decrease the distance between the particles, you increase the Coulombic force. So if you want to increase the force between particles, you have highly charged particles that are close to each other. Okay, next is the Bohr model. It's also called the planetary model. All right, now this is an older model of the atom. Models are used to explain the properties of an atom, or explain really the properties of anything. This isn't the current model of the atom that we use, but you want to know about it because it's useful to help explain some of the concepts. So you don't need to know a whole lot about the Bohr model. The Bohr model is that electrons move around the nucleus only in certain allowed circular orbits, kind of like planets around the sun. So this correctly fits the quantized energy level of the hydrogen atom. What do we mean by quantized energy level is you have electrons on a certain energy level. If they want to jump up to a higher energy level, they need to gain a quantum of energy. Now, you don't need to know that, okay? You don't need to know that, but that's kind of the current model of the atom. As an electron becomes more tightly bound, its energy becomes more negative relative to the zero energy reference state. As the electron is closer to the nucleus, energy is released from the system. Okay, so what that means is electrons have a certain amount of energy. So you have an electron on this first energy level close to the nucleus. So electron on the second energy level, it's farther away from the nucleus, it's going to have more energy. So what this kind of boils down to is if you have electrons that are farther away from the nucleus, as in higher energy levels, they're going to have more energy. So when you're referring to the energy of an electron, the farther away from the nucleus, the more energy they have. Now, what you don't want to do is get this confused with binding energy. Binding energy is a Coulombic force between the nucleus and the electron. And the closer the electrons are, the greater the binding force. So the energy of the electron and the binding force are different things. All right, so please don't get those confused. So again, when you're talking about the energy of an electron, the farther away from the nucleus, the more energy they have. Okay, next we have the quantum mechanical model of the atom. That's the current model of the atom that we're working with. It's a very deep subject, and you don't need to know that much about it. But all the following information is referring to the quantum mechanical model. Okay, so we have orbital shapes and energies. So orbitals are regions of space that can hold electrons. Now they have different shapes. I put a picture of them there, but you do not need to know the different shapes of the orbitals. Okay, just know that that's where electrons go. There's 4 different types of orbitals. There's s orbitals, p orbitals, d orbitals. There's also f orbitals, which aren't pictured. Okay, and then within those different groups, there's some different shapes. Okay, but if you just remember S, P, D, and F, those are the different types of orbitals. Now the orbitals have certain amounts of energy, and again, the farther away the orbitals are from the nucleus, the more energy that they're going to have. So the lowest energy state for an atom is called the ground state. That's when all the electrons are as close to the nucleus as they can get. If we put energy into an atom, electrons can be transferred to a higher energy orbital. That's called the excited state. So the way you put energy into an atom, you can add electricity, like in a neon light. You can have an explosion, like with fireworks. You can have other solar particles hit them. You can burn them in a Bunsen burner flame, like the flame test. So there's lots of different ways. Any source of energy that you put into an atom, electrons can absorb that. And then when they move up to a higher energy level, that's called the excited state. But now electrons don't stay there. When they go back from the excited state back down to their ground state, they give off energy in the form of light.